Hello everyone, I'm pleased to introduce our paper entitled Distributed MPC for Comfort-Based Temperature Control in Offices with Hybrid Heating and Ventilation System using Limited Data Exchange. My name is Vahid Ehteshami Bojnurdi, and I am a PhD student at Aalto University. Nowadays, improving energy efficiency has become a major focus. A large portion of energy consumption comes from buildings. In Europe, more than 60% of building energy consumption is dedicated to heating, which makes improving their efficiency particularly important. One common approach for designing optimal controllers in such systems is Model Predictive Control or MPC. MPC can achieve high performance by solving an optimization problem over a prediction horizon. However, in large-scale systems, it often becomes computationally expensive and too slow for real-time implementation. To address this limitation, distributed MPC can be employed, where the overall problem is decomposed into smaller subproblems and solved in parallel by multiple agents. In distributed approaches, agents iteratively exchange information to collaboratively optimize the global objective. However, in large-scale building systems, sharing certain type of data such as occupancy pattern or internal heat gain may not be desirable due to privacy concerns. Therefore, agents must solve the optimization problem with minimal information exchange, which is the main focus of this paper. In this work, a sample facility is considered, where each room is treated as an individual control zone. A linear thermodynamic model is developed for each zone, capturing heat exchange with the outdoor environment and neighboring rooms, as well as the effect of ventilation airflow and internal heat gains. The control input for each zone include the space heating load and the ventilation airflow rate. In addition, the supplier temperature is considered as a global control variable, which is regulated by the central ventilation system. Each zone is controlled by a local agent that determines the control inputs. The objective is to minimize the temperature tracking error. Due to the system decomposition, the problem is both cost and constraint coupled. While conventional methods require sharing detailed information between zones, including occupancy, we preserve privacy by sharing only temperature information. A three-level cascade scheme is used, where each zone solves its local problem, updates and shares its temperature, constraints are updated, and the central system adjusts the supplier temperature. This process is repeated until consensus is achieved. The method is compared with a centralized approach and shows comparable performance. It is also evaluated under different weather conditions for a 25-zone case study, demonstrating reliable and effective operation. Before concluding, I would like to sincerely thank the Student and Young Professional Committee of the IEEE Industrial Electronics Society for their continued support. Your encouragement helps the next generation bring innovative solutions into real-world engineering. Thank you.